Well, thank you, folks, whether you're here or online. I'm glad to join you. Glad to be part of this Rocky Mountain Creation Fellowship. You guys do an important thing, promoting creation and Bible study and the flood and all those kind of details. Let me say hello from Indiana. That's where I do live. As Rob just mentioned, I've been at Grace since 1972. Is that 50 years ago? Just yesterday that I started there, it seems like, and it's been good. Friday night, a busy night, but we're going to take a look at gravity. Thanks for your interest in being part of our time here this evening. Let me start with just honoring a couple of individuals, people that you may know, Henry Morris and John Whitcomb, just because these two gentlemen, these pioneers, are responsible for a lot of us in our creation journey. And they were kind of out in front, waking the whole thing up, and did a great job. And so I just so appreciate these two gentlemen. And by the way, one reason why I went to Winona Lake at Grace College is that's where John Whitcomb was a professor. And so I was his next door neighbor, took all of his courses. We wrote a book or two together. We had fun playing ping pong and everything else. He always beat me. He was a master ping pong player, but just wonderful people. John Whitcomb died a couple of years ago, but has left a good legacy for a lot of us to keep studying. So for a while tonight, we're going to look in on gravity. I don't know how exciting that sounds to you, but we will open it up in that way. And I thought a good way to start might be just to make a few comments that have, and quotes from over time. So this first one we have here is from Isaac Newton, talking about gravity. So what does Isaac Newton say? Gravity explains the motion of planets, but not the one who set those planets in motion in the first place. Interesting quote. In other words, Newton was a godly man. Now, we're not sure all the little parts of his theology, but he knew his creator. That little quote came about 6 years after he had written his book called the Principia. And in that book, he had explained the motion of the comets and the planets and all of space. And, he had all figured out. It's a great book. And when he came out with that book, his friend said, well, Isaac, you've done it this time. You're explaining everything. I guess we don't need God anymore. And this quote was his reply, saying, I'm not replacing God. I'm just trying to show you some ways that God works through things like gravity. So I kind of like Isaac Newton. He's a good example to us. So I just got a few more comments as well that involve gravity. This next one is kind of humorous. We need some humor on a Friday night. In physical science, we have some basic forces, some laws of nature. And so I just kind of started a list of them. We have gravity, we have the electromagnetic force, we have the nuclear forces, and then we have duct tape. What would we do without duct tape? So I put that as one of our basic forces as well. Now, the next little comment that I have actually comes from Discover magazine. This is from a couple of decades ago. And this was one of their lead articles in this magazine. Gravity, the most mysterious force in the universe. And here we are decades later, and it's still a mysterious force as they continue to work on it. So that was an interesting article. I'm looking at some comments that have to do with gravity. This next one is another humorous one. It's a picture. Critters are fun to look at. And it turns out that cats are not bothered by gravity. And so it seems like they can do some strange things. And I don't know what the background of this story is, but it looks very interesting. But we better keep going here so we can cover some ground with gravity. So let's just see just exactly what this is and kind of define it. So, gravity, an attractive force between all objects. This formula here was put together, not the formula, but just the whole idea by Isaac Newton as well. And the letters we have in this gravity equation, you have Fg, that's the gravity force. Big G is a constant, the constant of gravitation, actually measured by Cavendish later on. And then we have M&Ms. This is an attractive force between all masses. We could have your mass there and the mass of the Earth, for instance. And then you divide by the distance squared. And you can do the calculation. In fact, if you would put in your mass and that of the Earth, and for the distance between us, you could put from the center of you to the center of the Earth. And if you put in the numbers, you would just come up with your weight, because that's the gravity pull of the Earth on you. And that's kind of how the whole thing works. So gravity, an interesting force. It actually keeps us on the ground and it tires us out. You get a little bit weary this time of day because all day long you've been standing up against gravity. We've got to lay down at night to kind of recover for the next day. Gravity acts everywhere. You cannot cancel it out. There's no anti-gravity machine. It's just what we have. Now I'm still looking at this formula here, and it's divided by distance squared. That's the way gravity diminishes. And you can draw a picture of that. It's called the inverse square law. You know what this means? If you double the distance, gravity would be 4 times less. If you triple the distance, gravity would be 9 times less. This is the same way that light or sound also diminish as you move away. And by the way, this inverse square law is why astrology does not work. Because gravity goes away as a square of the distance, and those planets are so far away already that their gravity has no effect on us. So much for astrology. You didn't believe it anyway, but this finishes it off as well. We are not influenced by any kind of gravity from those space objects at all. That formula we were looking at, there's some interesting symmetry in nature. Let me just put a couple here together. There's a repeat on the left of our gravity force, and on the right is the electric force. It's very similar, isn't it? In that case, the 2 Q stand for plus and minus charges, but again, it's divided by distance squared as well. This symmetry in nature, it shows God's pattern, the way he put a lot of these laws in place. Now, I'm still thinking about that denominator in that formula, that gravity goes away as distance squared. That actually fits 3D geometry, space. It's the way things spread out. But some folks are a little bit bothered by that equation. Why is it exactly R squared or D squared? In a chance accidental universe, why isn't it like 1.99 or 2.01 or something like that? And so that really worries some people. And a while back, there was a magazine called Science News. This goes several years back. And they had an article about gravity, and they said, you know, that formula divided by R squared is too neat. And so they've done experiments to carefully measure gravity on a small scale in the laboratory to see if it really could be 1.99 or something like that. And they measured it, and it comes out to be exactly 2 out to 5 decimal places. And that's as far as they could measure. I'm sure that it's exactly 2. It's the way God put the whole thing together. So much for being too neat. It is neat, but it's part of the whole creation story. These physical laws that are all put together. Now, I mentioned this fellow, Isaac Newton. You know, we've heard the story that maybe like an apple fell on his head. There's no truth to that. It has not been backed up at all. Although in Newton's writing, he does mention watching an apple fall to the ground. And they think they know what tree that was. And they've taken branches off that tree, and it's still growing in England. And you can go take a picture of it. There's a picture on the screen. They call it Newton's tree. And I forget which campus it's next to. I have not seen it. But this goes on 3 centuries later, kind of a part of that whole famous story. So anyway, there's Newton out in the countryside. You know, there had been a plague at that time, and they closed all the schools, and Newton went to live with his uncle. So there he is out in the countryside, and it looks like he's looking at the moon in that picture. And he came to realize that the same force that pulls an apple to the ground is pulling on the moon and keeping it from escaping. That was a major thought. that gravity, this pull of the earth acts everywhere, on the earth with an apple, and even in space where the moon is. And then he went further as he was exploring this, and it's kind of interesting what he did. So this next slide gets a little bit technical here, but stay with me. On the left-hand side, down in the corner, we have planet Earth. And you know, things fall to the ground. You will if you fall. And we talk about the acceleration due to gravity, 9.8 meters per second squared, or 32 feet per second squared. It just comes up so often, we just call it G for gravity. It shows up all the time in physical science. It's just the way everything falls to the ground, other than air friction if it comes down. Now, Newton realized that the moon was way out there, about 60 Earth radii. If you take the Earth radius, multiply by 60, and you'll get the moon's position. And he realized that gravity went away as the square of the distance. So he took that 60 and squared it and said that the Earth's gravity out where the moon is must be 3,600 times smaller. See how he did that? And that's the part on the right part of this picture. And so the moon does feel the Earth's gravity, and it does accelerate, it does fall toward the Earth, but much less. Take 9.8 divided by 3,600, and you have that small number that's on the screen. So the moon does feel the Earth's gravity, and it's falling toward the Earth, but of course it does not get any closer. Actually, the astronauts on the space station, they also feel this gravity, and they are falling toward the Earth. They are not weightless, they are in free fall toward planet Earth all the time. So why don't they hit us? Well, you know, part of the story is that we have this tangent motion. And so if you get going fast enough, you fall around the Earth rather than hitting it. And you have that kind of balance. And if you would speed up the moon or slow it down, it would kind of adjust its orbit, get closer or further away. That's the whole way that satellites work. So round and round it goes as it's falling around the Earth instead of getting any closer. What a neat system this is. Now, let me give you a couple of thought questions. What would happen to the moon if all of a sudden Earth's gravity stopped? What if there was no more pull on the moon? What do you think it would do? I need to try this out. I brought my tennis ball. Amazing what's hanging around here. And so let me get this thing going here. This ball represents the moon. And my hand will be the Earth, and we'll get it going in orbit here. Of course, it takes the moon a whole month to go around the Earth, but here it goes. Let me get this a little bit longer. So I said, what happens if gravity quits? So what I need to do is let go of the string when it's at the very top, because my string is kind of doing the same thing gravity does. So if I let go when this is at the top, is it going to go straight up and hit the ceiling? Is it going to come down and hit me in the forehead? You hope so. But let's see what it does. I'll let this go on the top here. On 3. 1, 2, 3. And it comes back to me. It takes off on a tangent. If there's no more gravity force pulling on it, we also call that the centripetal force, there'll be no more circular motion, and off it goes. And there would go the moon sailing off into the sky. Of course, actually, if the Earth's gravity quit, we'll have our own problems down here below. We'll go floating around as well. Here, let me give you another thought question. What would happen if all of a sudden the moon stopped in its orbit? Because it's moving pretty fast, you know. What if all of a sudden it just became static up there with no more tangent motion? You got the Earth, you got gravity, and there's the moon. The moon would start falling directly toward the Earth, and it would get closer and closer, and the tides would get larger, and you'd say that moon is getting bigger in the sky. And if you do the math, it's a little hard. It involves differential equations, but in 5 or 6 days, the moon would hit the Earth, and that would not be a good thing. It would be the end. But of course, it doesn't happen because gravity keeps on going as well. So anyway, we're kind of looking into gravity here and seeing some of the details and how God makes the whole system work. But I like these thought questions. So here's another one for you on a Friday night. What if tomorrow, this weekend, we had to shut down gravity, the gravity pull between the Earth and the moon? It's going to be down for repairs. Oh my goodness. Now, we don't want to lose the moon. And so instead, let's build a steel cable from the Earth to the moon. And so kind of like a string so the moon doesn't get away. So we're going to replace gravity with a steel cable. And you're saying, this isn't going to work. The moon is moving and it's going to get all tangled up. Don't worry about the details. I'm replacing the gravity force with a steel twisted cable, the way they make the strong ones. So I'm wondering, how thick does this cable have to be to replace gravity? We're trying to get an image right now of the strength of gravity. So here's my picture. I was thinking about this problem. How do you like my cable there? I'll make this a multiple choice. The needed diameter of a steel cable to replace Earth-Moon gravity, it comes out to be 600 something. Choice A, 600 inches. That's 50 feet. That would be the whole length of this auditorium, the thickness of the cable. Or is it maybe 600 feet, which is larger than this building, the diameter of a cable? Or might it be 600 miles, which would stretch from here into Iowa? Okay, there's your choices. If you're near someone, get your answer here. What your choice is going to be, and then I'll reveal the answer. What do you think?
Inches.
And someone says, I don't know, and I don't care. It's kind of fun stuff. This is this physical force we have. You know what the answer is going to be? It's C. It's 600 miles. There's not that much steel available on this planet to build this thing, even if you could. This is showing the strength of gravity. It's huge. It's 10 to the 22 tons. This thing adds up, the force between the Earth and moon. We pull on the moon, keeping it here. The moon pulls on us and causes the tides. And that's where you can start to see the magnitude of this force, this cable, when you think about the tides, where billions of gallons of water are pushed around by the moon's pull. And so just a little thought here on the tides for a minute. Maybe some of you have been up to the Northeast, up here in New Brunswick, where we have the Bay of Fundy, where we have the highest tides in the world, 50 feet from low to high. I mean, that water goes back and forth. It's in resonance in that long bay there, this Bay of Fundy. And it's kind of an interesting place showing the power of the gravity force pulling on the water. When we were up there, we noticed that when the tide is in, the boats float. When the tide is out, they're sitting on the ground and you can work on them. Major changes, 50 feet, that'd be higher than the height of this building. That water moves around. And in that same area, they have these provincial parks up in Canada. And when the tide is out, you can walk on the bottom of the ocean. But you better watch out, because 6 hours later, the water's coming back. You better have a kayak or know how to swim, because it goes underwater rather quickly. Back and forth the water goes on a huge scale. The strength of gravity is just so impressive. So we're talking about the forces of nature, and I'm going to show the list again, this time without duct tape. But anyway, this is kind of what they look like, the known forces from the physical science world. We have what's called a strong nuclear force. It's quite strong, but it's quite limited. And then you have the electric force and the magnetic force. We've all experimented with magnets. And there's the weak nuclear force, and there's gravity. And look who loses. Look who's in fourth place. Gravity is much weaker than these other forces. So how can I have that big cable? What's the deal here? It's kind of interesting. Well, those two nuclear forces are very short range. They only act inside an atom, inside the nucleus. So you don't see much of them. And electromagnetic forces like magnets or electric charges, you know, there's always a plus and a minus. So they tend to cancel out. Nothing cancels gravity. It's always attractive and it's always there. And that's why it dominates on the scale of space. So it might be in last place in that list, but it's still very impressive and takes over when it comes to the moon, planets, things like that. We're talking about gravity here, folks, and let's go to the base here. What is it? How does it work? What holds us on the ground? There's no strings attached, nothing between here and the moon that we know of, and yet it just keeps on operating. So there are two popular models today on how gravity really operates. One is called particles, gravitons, and the other one is called curved space. And so these are worth looking at for just a moment because this is kind of our current understanding. So this first one involves gravitons. This idea was first suggested back in the 1930s. So it's not exactly new, it's going on a century old. These theoretical particles called gravitons are thought to move between masses. And they somehow tie them together, including you and the Earth, or the Earth and the moon. They somehow cause a gravity attraction like a stretched rubber band. Graviton particles would have no mass, they would have no electric charge, and they would travel at the speed of light. This is what all our theoretical understanding gives us. In fact, that description of these little particles is something like photons. Remember that particle of light that travels at light speed? Well, I want to tell you that so far, graviton particles have not been detected, and they've been looking for them for decades. In fact, they may not even exist. It's just one possible model that invisible particles tie us all together. But that second idea, that somehow space is curved and this causes gravity. Now, you've heard this idea before, and there's interesting pictures. So just to visualize this, suppose that we have a trampoline. You bounced on one sometime in the past. So take this trampoline, maybe in your backyard, and right in the center of it, put a bowling ball. So that's going to push down, it's going to make a depression, it's going to make a low spot on the trampoline. Then take a tennis ball and toss it on the trampoline, and what it'll do, it'll kind of go around that bowling ball because it's kind of caught on that slope. Now, it might fall in and hit it after a while, but can you see how it would be trapped? So the suggestion is that all these space objects make depressions in space, they make low spots to trap other objects. For instance, the Earth and Moon. There's the Earth, which is making a dip in space, and there goes the moon, kind of caught on the edge there on that slope, and round it goes, and like the tennis ball might hit the bowling ball, but there's no friction in space, so it just keeps going on round and round. They draw interesting pictures of this kind of stuff. Here's an extreme, if you have what's called a black hole, which is a collapsed dead star, where gravity really gets strong, so strong it looks like the dip just goes, I don't know where. It's like a hole in space, and stay away from those. Those wouldn't be good for you. Now, even on a Friday night, some of you folks are thinking, wait a minute, you've lost it. I can understand a trampoline. It's a two-dimensional surface, and you can put a dip in it, okay, and a ball will get caught. But I'm talking three-dimensional space. You can't visualize that. It becomes abstract. But that's kind of what I'm hinting at here. And when they try to draw pictures, they're kind of interesting. Now, here's planet Earth, which is kind of wiggling all the lines of space around it as if wherever you are, it's making a low spot. But suddenly it becomes 3D. So it's stepping on the trampoline. But so this whole thing goes. So we didn't spend much time on the gravitons, doesn't see much evidence for them, but the curved space is worth thinking about a little bit more. Now, along with this idea of curved space, it has also been suggested for a long time that there are ripples that kind of move through space, and space kind of gets bumped together, and then it gets spread out, like waves, like gravity waves moving through space, almost like a water wave. And you know, in support of this, gravity waves were detected in 2015 That's 7 years ago. And so this is adding to the idea that curved space is part of the whole story. It's interesting how they do this. This is called an interferometer. This is a big time experiment. And for short, I'll just call it LIGO. You can see all the other words that go with it there. There are two setups like this. One is in Washington State and one is in Louisiana. And what happens is a passing gravity wave, this compression and an expansion of space, goes ripping through this area, and it changes the length of the arms of these experiments, and they can measure that. And they'll measure both of them at maybe a little bit time between them and know that something happened to space, that it compressed for just an instant. And that's how they measure these gravity waves. We think that they're caused by violent activity in space, whether it's neutron stars crashing into each other and whatever it might just be. And by the way, these compressions, and they've now measured hundreds of them in the last 7 years, they're very small changes in space, like the size of a nucleus, which is really small. But I'm just imagining one of these gravity waves passing right through our auditorium here. For one instant, you are a little bit closer to the person sitting near you. And the next instant, you're further apart again. There's this ripple that moves across. But we don't notice it because we are embedded right here in space, so we're part of the whole story. But this is the kind of thing that's happening. But if it only moves as much as a nucleus, you wouldn't notice it anyway. But that's kind of how the whole story works. Well, these gravity waves are found to travel at the speed of light, which is also the propagation speed of gravity. Now, Newton thought that the gravity force was instantaneous, but experiments have shown that the force of gravity, even caused by the moving moon, it travels outward at light speed. There's something very fundamental about light speed. Now, you know what this means? We are held in orbit by the sun, the sun's gravity. What would happen if all of a sudden the sun would disappear? It's just gone. Annihilated. No more gravity pulling on the sun or on the earth. But the earth is quite a ways from the sun, 93 million miles. In fact, at light speed, the earth is like 8 minutes and 20 seconds from the sun. So if the sun would disappear, we would keep circling where the sun was for 8 minutes. And then the last of the gravity would get here and we'd take off in a straight line. You get that idea that even the gravity force travels at light speed. Very interesting. That was a complicated experiment, but it's fairly well proven. So anyway, curved space seems to be part of the whole story of how gravity works. Now, let me just kind of qualify all this. Whether gravitons or space curvature give the best description of gravity, we don't know. And it might be similar to the way we look at light. We don't really understand light either. It seems to have a wave nature and a particle nature. So maybe gravity has both a graviton nature and a gravity wave nature. We're just not sure. And whatever the case, these models, graviton, gravity waves, they don't explain how these things exist in the first place. It's just a description. The more I look at science and nature, naturalism cannot explain the ultimate origin of gravity or anything else. They always start with something. So another good, vote in favor of a supernatural creation. Boy, this is all getting a little bit deep here. I lost you on the gravity waves. So let me back up and let me give you just a couple of simple thoughts when it comes to gravity, because we all live with it. It's just good to understand. So I've got a few questions for you. Here's the first one. Are you slightly taller in the morning or in the evening? Because our height varies a bit. The winner here will be in the morning, because all day long walking around, You're banging it against gravity with your joints, and it compresses your bones. And so the typical person is about 1 centimeter taller in the morning after you've laid down and your bones have recovered. You might check that out. Some people as much as 1 inch. So maybe you're not shrinking. Maybe it's just gravity doing that temporarily. So there's the answer. It's in the morning. Next question. I've got questions. You would weigh more at the equator or at the poles? At least you only have 2 choices on these, folks. And the answer is going to be you will weigh more at the poles, because the Earth, that globe, is not perfectly spherical, but it's flattened, kind of like a doorknob. That's exaggerated, but it's flattened a bit, which means if you're at the North Pole, you are closer to the center of the Earth than you are at the equator. So if you want to lose a pound instantly, go to the equator. You'll be about 14 miles further from the center of the Earth. You divide by distance squared, so you'll lose a pound. Then when you come home, you'll gain it back again. But anyway, that's having to do with the geometry of the Earth, and back to that old formula, the d squared. Did I say that right, that the poles are closer to the center of the Earth than the equator is? Boy, the questions go on. Here's another one for you. On the top floor of a high rise, would you weigh less or more?
Less.
You're right, it will be less because you are further from the center of the Earth. You got it. How that works, that's all just a review of the gravity force, how it operates. Hey, here's just a few more ideas about gravity, because it's just all kind of neat stuff, how it all works and is so faithful. Starlight coming in our direction toward the Earth can be deflected by the sun or by stars. And so this is kind of a diagram showing how stars, distant stars, may not be exactly where you see them in the sky. Because if that light comes close to another space object, it'll feel its gravity, or it'll feel its curvature of space and be deflected. Now that deflection in this picture is less. Well, that's much less than 1 degree, so you don't notice this. Astronomers get involved with this, but stars are pretty much where you see them. But there's this slight little shift due to this whole idea of that light can feel gravity. It's, just the space curvature idea. And sometimes this could be more dramatic. So this is a diagram. See if I can catch this here. There's a faraway galaxy on the left, and there's Earth in the lower right. And in the middle is a central, looks like something bright, like a galaxy. So now that distant galaxy, the one way on the left, it sends out light. And as it has to pass through that middle area, its light can be deflected. They call this a gravity lens. There's no glass, but just the space, the gravity can curve the light. And then finally, the light gets maybe to where the Earth is. And if you look at those 2 tan lines, you can actually see the same object in 2 different places because you're just following that line of sight. That gets really interesting. Now, you've heard of the James Webb Telescope that was sent up this year. This is one of its very first pictures. That thing is 1 million miles away, and it's taking some close-up photos that we hadn't seen before. In this picture, the object in the middle is this galaxy kind of between us and distant objects, and it's deflecting the light. And so then there's another galaxy way out on the left. And as it goes around that middle light, well, I kind of drew some wiggly lines around it. Those are all of the same object, but its light is being shifted, it's being bent different ways, and then it comes together on the Earth. And in that case, we're seeing the same object in 4 different places. That's all due to this gravity deflection of light, getting rather complex. I'm glad that astronomers can keep track of all of that strange business going on. So anyway, yeah, that's a recent picture from the Webb telescope. And we're looking at some odd things about gravity, but really it is all kind of fairly basic. So let me show you another one that's kind of interesting. It has been proposed that we could use gravity for transportation. It will burn no fuel, no gasoline, It won't take any solar, it won't take any electricity. It won't make any pollution. It'll be free transportation. This idea was proposed 100 years ago by a fellow by the name of Lewis Carroll. Now, he's the guy who wrote Alice in Wonderland. He was also a mathematician, and he was a futurist. He had these ideas of what could be. And so he said, here's what we need to do. We take planet Earth and we drill holes through it, all the way from one side to the other. These are tunnels, and this diagram just shows several of them. Now, it's not that the Earth is going to fall apart. These are just small tunnels, although they might be big enough to hold a capsule. And so he said we could design these capsules, connect them together, and have trains that fall through these tunnels, gravity trains. Now, can you just imagine this if you could pull this off and have this tunnel all the way through, starts in Denver, comes out down in Australia? Boy, you get to the edge and you look in this hole, that's a long ways. It would just look kind of dark. But if you're in a good capsule where you're secure, you get in it and you drop into this hole. You're falling down a hole and you'll go faster and faster. By the time you get to the middle of the Earth, you are really moving fast. And then the second half of this trip, you're actually coasting uphill because you're falling out of the hole. And if you don't bang into anything, if you could somehow survive, you could get to the other side. And when you do the physics of this, it takes 42 minutes to go all the way through the planet. Does anybody see a problem with this so far? It's a little warm, Paul says. Well, of course, the inside of the Earth is molten. This is impossible. The deepest hole that we have dug is about 8 miles, and that was a drill string. That's a well hole, let alone a big tunnel that you could go through. So the whole thing is crazy. But Lewis Carroll was a futurist thinking about this. And so he said you could have this whole network of tunnels. And so from Denver, you could go any place in the world in 42 minutes. And every major city could have these. The whole Earth could be just honeycombed with these things. Wow, what a deal. And you're using gravity, so you're just falling one end out the other, and so it would be free energy. I agree with you that this is impossible, but this fellow, this author long ago, just had this interesting idea. And I must tell you, sometimes I wonder about this. Now, we all have different ideas on the future, the new heavens and the new earth, and what it might be like. But you have this potential here of free travel, 42 minutes, using gravity. And maybe we can't drill a hole like this today, but maybe someday. Are we getting a glimpse of maybe what the future Earth could look like? And then you could do this on other planets. It's craziness, but it's amazing the kind of things that people come up with. So I'm hitting all different areas of gravity tonight, and that's just one of them. And let me just kind of close up with a few more thoughts. Let's become theological here for a little while when it comes to gravity. So let me just try a few basic questions on you. They kind of look like this. And yeah, you can see what the questions are. Let me just kind of react to these. Make my notes on this as well. And so this would just be my kind of suggestion, perhaps, of what the answers might be. I'm not sure where all my notes went on this, but anyway, we can look at them together. Our first question here, does gravity have an origin? Does it have a start? And of course it does, and I have a yes there. And our verse is Colossians 1:16, for by Christ all things were created, visible and invisible. I think that includes gravity. It had a start. Now, whether gravity was set up during the creation week or at the end of the week, it fits in there somewhere at the beginning. I would say that during the whole creation week, God was inputting energy into this universe from his infinite supply. So we didn't have conservation of energy yet. God was putting it in there. And ever since the end of creation, things have kind of been coasting and have been constant, including gravity. So that was the next thought there. When did this happen? And I just kind of hinted at that. It had something to do with either during the creation week or at the end. I like to think about these laws, physical laws of nature, and just when they came, how it all worked out. The next thought here, is gravity self-sustaining? Does it run on its own? Well, I don't think so. In fact, there's this next verse, Colossians 1:17, which says that it's by the Creator that all things consist or hold together. These laws don't run on their own. No laws do. Somebody must enforce them and hold them. And I think the Creator has a continuous part in this. There's the verse that we're kind of getting at right there now. And you know, this idea that the Creator's involved with the present day. Let me give just another thought here. There's a big question today in astronomy. It involves these galaxies and why they exist. Because when we look at these stars, this is Andromeda, ours is the Milky Way, just a whole whirlpool of stars. As we measure these big objects, they're like islands that just fill up the universe. There does not seem to be enough stars in those things, enough gravity to hold them together. I mean, they're turning, they're circling, and they're like a merry-go-round, and they're going fast enough that it seems like they should disintegrate. The galaxies should be gone, and yet they hold together very closely. And so they talk about some things in the galaxy that they can't see. They call it missing matter, dark matter, hidden matter. And it gets rather humorous because the amount of missing matter for the whole universe is somewhere between 60% and 90%. You mean to say 90% of the universe seems to be missing? It's kind of embarrassing, but that's what they've come up with. So I think about that mystery. And then I think about that verse that says, by God, all things consist. That tells me that at some point, the physical universe must interface with the spiritual world. Maybe this hidden mass is not even there. Maybe it's God's hand holding this whole thing together. Now, I've got to be careful because they keep making new discoveries, but they've been looking for the missing matter for decades, and it's not there. So I don't think that any of this stuff is self-sustaining. I think God's got his hand in even operating gravity. I will say this, if our Creator would turn his back on this universe for one instant, can you imagine what would happen? Chaos. The whole thing would go to pieces and it would be all over before our very eyes. But that doesn't happen. Our Lord is faithful. Does the law of gravity change? I was just trying to hint at some theological implications to gravity. Well, all I can tell you, my world is physics. We carefully study the speed of light. We can measure the strength of gravity, and it's very constant. And that's what that verse in Psalm says, that God's faithfulness is shown by the heavens, by the regularity, by the constancy of this nature that he has set up. So I'm giving that a no, if the laws don't change. And it's for that reason that we can just plan ahead on certain things like eclipses. So I just was going to mention here, once in a while, the moon moves through the Earth's shadow, and they call that a blood moon. Actually, it just gets kind of orange or pink. And we have one of these coming in 2 weeks, 2.5 weeks, November 8th. There'll be a partial solar eclipse that you can see here from Colorado. Everybody can see it. Not a full eclipse, but partial. So that goes along with the full moon. So you might watch for that. And we know for the very minute when it's going to start and when it's going to stop, because these laws do not change. They're constant, at least during our era. I like that it's dependable. There's one other kind of eclipse that kind of catches our mind. That's a moon eclipse. What's the other one when the sun gets covered up? A solar eclipse. Now that's a little bit more rare. And but we're living at a good time right now in this world and in our lives. And there's going to be an eclipse in a couple of years, which does not go through Colorado, but it's going through Indiana. So come on over and join us. This is April of 2024, and right along that path, there's going to be a total eclipse. It'll get dark at noon for about 3 minutes. The stars will come out. It'll get cooler, and then the sun comes back again. It's so predictable to the very instant. Now, it may be rainy in Indiana. We won't get a good look at it, but we're hoping that we can have a time to see that. I went to see the last eclipse. There was one 4 years ago. It was down in Kentucky, and it got dark in the middle of the day, and the stars came out. And then we stood there in a group, and an owl flew past. He thought it was night, so he came out. And then 3 minutes later, it got bright again. He was probably confused. Very interesting what this happened. But I didn't want to leave out Colorado. So if you can wait till 2045, there will be a total solar eclipse cutting right across Colorado. Can you hang on that long? It's 20 some years. So these are quite rare. There won't be another one in North America, I think, until 2099. So this will be a good one to watch for. So along that path is where the sweep of the earth, where the shadow cuts across the land. So it's good things coming here as that happens. Anyway, that all went along with that theological question of do they change? And then I got that last one there. Is gravity really understood? My goodness, we just spent a whole hour talking about it and we've just confused ourselves. You know, Stephen Hawking, now he's passed and gone, but he did a lot of writing. And Steve Hawking would say, you know, someday we're going to have a law of everything and then we'll know everything. And that was what he was working on. And I'll have to say, sorry, Stephen Hawking, no. In this world, we're never going to know everything. And there's that verse in Job 38:33 where God is talking to Job. And he says, Job, do you really understand the laws of nature and how everything works? Of course, the answer is no. And even with our intellect today, there's still lots we don't know. We don't even know whether gravity is a graviton or a wave or something in between or something else brand new. So we can't understand gravity completely, but we can certainly appreciate that God put it together for our well-being, even in a world that's far from perfect. We can see how this whole thing's been made for our benefit. Hey, that's it. We did a real quick look at gravity. We had the formula for it. We talked about gravity trains. I can hardly wait for that one. And there's some theological implications as well. So anyway, that's where it goes. If you folks may have a question or a comment, I'd be glad to react to that as well. Rob, do you want to, if anyone has a question, maybe you could mic that for them? But go easy, because I don't have any more answers.
Check, 1, 2, 3, 1, 2, 3, check. Okay, so what we're going to do is if you got a question, let me know about it. I will rush this mic over to you and ask your question into the mic so that we can get it on video more easily. And, you know, come up with some good questions. Let's try to put Dr. DeYoung on the spot, okay? So, you know, come give him something, you know, really to chew on. So, all right, here we go. So.
A couple of years ago, I think it was, we went up north to the next state, whichever that is, and there was an eclipse that we experienced. I'm wondering, was that not an eclipse? The moon was in between the earth and the sun, I believe, and it got dark. Any of the rest of you remember that?
When?
2-3 years ago, and we went up north.
We're south of Yellowstone.
Yeah.
We're south of Yellowstone.
Anyway, and there was an eclipse.
Yeah, you're describing the last eclipse. I think that was 4 years ago, and it swept across the country. I went down to Kentucky to see it, but it did head north. It didn't go through the Midwest, but maybe up where you were.
Yeah.
And I think that was a total eclipse, and it got dark. You know, partial eclipses are much more common, but the total ones are very special. So that was great that you could experience that. And by the way, isn't it interesting that the moon can cover the sun? I mean, after all, the moon is 400 times smaller than the sun, but the moon is also 400 times closer than the sun. So they have the same size in the sky, so one can cover the other one. Nothing else in the solar system is quite like that. Thank you, Lord, for even making that kind of alignment that we can experience eclipses, which are part of the beauty of nature. I'm glad that you saw that. Did you know that was coming, or did you take it by surprise?
No,
You're all set for it.
coming and we actually traveled up there.
Yes. You know, when there's an eclipse, lots of people go out to be on that path, and then they have huge traffic jams, but you already have enough traffic here in Denver.
Okay, we have a Zoom question.
Actually, no, my question.
Oh, we have a question, which Fred is gonna ask.
Thanks.
For the Zoom operator question.
Have you thought about, I find this whole quantum entanglement is fascinating, where it's really almost suggests there's information at play, so the two particles know about each other across the entire universe. Have you ever thought about that in the context of gravity? Maybe there's information at play and it can, I don't want to say travel faster than the speed of light, but we know that with quantum entanglement, something's happening faster than the speed of light.
Okay, this question involves the quantum world and this strange phenomenon called entanglement, whereby two particles can kind of get familiar with each other. And then when you pull them apart, if you wiggle one, the other one responds, even if one is on the East Coast and one's on the West Coast. And so there's this strange, mysterious web of connection between particles. And that doesn't even seem to be the speed of light. It seems to be instantaneous. So very little is known about that. That almost starts to sound like the idea of gravitons, that there's invisible particles going back and forth. Now, entanglement is it shows how little we really know. The quantum world is the frontier, at least of my area of physics. We got a lot to learn, and it's a mystery. Whether that could somehow relate to, great, now we got two mysteries. We got gravity and entanglement. I don't know if they're coupled or not.
I've got a question.
We were at Yellowstone watching the event, and one of the things, we had telescopes set up and they had you shine the shadow onto a placard, a white card, so that you could see it. And one of the things that I saw that was really amazing was that we'd be standing underneath some trees. Well, the light would shine through the leaves of the trees. And by doing that, we ended up seeing that picture of the eclipse at every light spot where the light shines strongly through the leaves. It didn't matter how the pattern was, but I saw, you could see like 20, 25 of these images on the ground. You could see how it changed with time as the light came through there. Just from the distance of light passing through the leaf opening of the sun all the way down to the ground to see it on the ground. That was just an amazing thing.
Yeah, so you're looking at an eclipse with some tree leaves. So you saw 25 eclipses.
So
That's all the better.
That's what I saw. It was basically 25 eclipses that were on the ground.
Yeah, the leaves, the openings, small openings are acting like a pinhole camera, almost like a lens, and then refocusing the light on the ground. That's an interesting phenomenon. I'm glad you got to see that.
That was the most amazing thing I saw.
Yeah. When people see eclipses, even worldly people, they're always impressed. It makes people tend to be quiet, because it's just a majestic part of nature. When anything unfolds in the heavens, it certainly gets people's attention just because of the grand scale of it. And I think it's for us to enjoy most of all.
Along with what our friend was saying from Yellowstone, we live up in brush. And so we didn't have an optimum spot, but we could see partial eclipse. And one of the things that I did, I realized that it had a small hole, you could show it. So I went in the house and got my wife's, I think you call it a colander. And you put vegetables in and it drains it out, it had a whole bunch of little tiny holes that were probably about a 1/16 of an inch in diameter. And so I held that thing in the sun and there was all those little partial eclipses on the sidewalk. And I thought, that's pretty cool to see that. That's part of the solar eclipse.
So Paul, everyone else is looking at the eclipse with telescopes and binoculars, and you have a kitchen utensil?
Yeah,
I like that.
we're very practical in brush.
Good for you and your wife.
Yeah, wow.
I like that.
But I had another question, and that had to do with gravity. And I believe I understood you to say that it's not decreasing, it's constant. It seems to go against the whole world and everything else seems to be running down. And why isn't gravity running down?
Well, things certainly are running down, both socially and economically and
Well,
everywhere else. But when it comes to these physical laws, as best we can tell and through the years, those are constants of nature. So yeah, the second law says things wear out, energy becomes unavailable, becomes more expensive, but that's all separate from these physical laws. And by the way, even if energy becomes unavailable, it's still there, energy is conserved, it's constant. That's really what makes life dependable. Otherwise, you'd never know when you're going to run out of gas. So it's good to have these laws. Yeah.
Thank you.
Would you like to
talk about the design of the universe in terms of gravity? Not just gravity's a part of that, but God had to set things up in our solar system. Some satellites go one way, some goes the other way, some are even different. He set it all up for a specific reason. I didn't know whether you want to comment on that.
Well, you're describing the great variety that there is even in our solar system, let alone our galaxy and space and on and on. When I look at our solar system, we've got 8 or 9 planets. There's no two alike. They have different speeds, different tilts, and I think God's put enough variety in this solar system that it just frustrates any natural origin theory. Things just aren't the same. He's an artist, infinite, and there's just no end to the variety. And there's very little that we know about deep space, but we know there's different kinds of stars. There's red giants, there's white dwarfs, neutron stars, pulsars, and there's probably many more that we haven't even detected yet. The variety just never ends. That's kind of what you're describing there, the design. And God's got his own purposes for a lot of it. Yes. Good reminder.
I had a question about the living planet. Guillermo was talking about the only things you can see about the sun when you have a full lunar eclipse, I think. Can you say some of the things that you could see only when there was an eclipse?
Well, the question is, what can you see in the sky when there's an eclipse? Well, you're seeing then the stars that are usually hidden in the daytime sky, and all of a sudden it becomes dark. And so for at least for about 3 minutes, you can see stars that you wouldn't see otherwise. Now you'll see those same stars 6 months later at night, but you're seeing day stars, which is kind of intriguing. And really, when you cover up the sun during the daytime, that's a good chance to see the planet Mercury, which is always close to the sun and is very difficult to see. I mean, when the sun goes down, Mercury goes down. But all of a sudden, when you cover up the sun, a great time to see it. And there's that bright light real close to where the sun was.
Do you see lunar flares at that time?
Solar flares. Yes, you can. You can see the edge effect of the sun. Of course, if there are flares occurring, I think we saw a little bit of that. I'm trying to remember one that I saw 4 years ago. What really amazed me, the sun got covered up and it was dark and we were all just, as many of you were just watching it. And as soon as the tiniest part of the sun showed up again, it was just like a flashball. It was so bright because you don't usually look at the sun, but when the tiniest sliver showed up, you just could not look at it. It was just the most intense light I've ever seen. It reminded me what the sun is really like. So that's the other thing, that it gets cooler when the sun's covered up and it does become dark and the stars and the owls and whatever else might happen. But it's mainly just a good time to kind of meditate and think about God's control of it all.
I was intrigued by just thinking about the fact that gravity would travel at the speed of light. And if there's a theory of relativity then that's being developed relating to gravity, that its speed would be the same for all observers, the tremendous implications that has with light, with Einstein's general relativity. And of course, general relativity relates to gravity, but I'm just trying to figure out what the implications would be that gravity travels at the speed of light, presumably same speed for all observers. Any thoughts?
Let me know when you figure it out.
Okay.
Yeah, I'm not sure what to say there.
Yeah.
There are some areas of gravity, along with the mysteries, the speed of it, and the quantum side of gravity. There's just lots we don't know. Yeah, I'm not sure how that would interface with relativity. Speed of light is the speed limit of the universe. It's just a whole, at least in space. So whether that does for other observers, according to relativity, wherever you are, you still have that same light speed, and it seems to be part of the structure. I'll have to think on that question that you asked. Thank you very much.
All right, well, this is a bit of an elementary question, but it is Friday night and I don't like physics, so I will ask it anyways. The question would be, when you were talking about the curving of space and how that can affect gravity, you were talking about how on a trampoline, if you were to put a ball in the middle and put another tennis ball, it would fall toward the ball. But then you said something, just a one sentence real quick after that, about how in space there isn't friction. So the tennis ball, or in this case, the moon, isn't going to just fall to Earth. And I'd like you to maybe expand on that a little bit so that I don't have to go home and figure it out myself, because that's a lot of work.
So that's an elementary question.
Extremely.
Yeah, as soon as you talk about a trampoline that we can all relate to, the ball is rolling on that fabric and it's going to slow down and fall into the bowling ball and quit, because we always have friction. That's why, nothing on this earth goes for very long. But in the vacuum of space, especially something as big as the moon going around the earth, the friction is just not there. And so it just continues to coast through space. Now, if there were dust particles in there that could, it could capture and slow down, and maybe on a trillion-year time scale that could happen, but certainly there are, in young Earth view or evolutionary view, the friction is just not there.
Okay.
And so all the planets keep going around the sun unless they crash into something. It's a friction idea.
Gotcha. Thank you.
I was also intrigued by the idea that gravity travels at the speed of light. And it made me think, if it's traveling at the speed of light, it's traveling, so it has to have a point of origin somewhere. So somehow there's something creating this force that's moving outward from that point of origin at the speed of light. And it seems to have some other properties too, like we were talking about the tidal force of the moon on the earth breaking the earth slows down as a result. And there's a transfer of energy to the moon, and it drops further away, so its orbit gets a little bigger as it picks up the energy. So it seems to imply there's a natural point of origin for something that's traveling at the speed of light, and it has the ability to convey energy across the universe as well, at least between the earth and the moon, the sun and the earth, etc.
So when we were thinking about Colossians 1:17, that God holds everything together, how do you reconcile a supernatural source of this where it seems that it's a natural phenomenon radiating from matter? And how it radiates from matter, I don't know, but it seems that Colossians 1:17 wouldn't fit the model for gravity.
Well, I hear what you're saying. Again, that verse that by the Creator, all things consist or hold together. And then I made the remark that it sounds to me like at some point, the spirit world interfaces with the physical world, if he's holding it together. Now, I want to be careful about putting the supernatural in there because we do keep making discoveries, but we've had a good look at that. Yeah, whether gravity needs some kind of beginning to launch itself, that goes back to the idea we don't know the origin of anything. We can talk about curved space, but why is it curved? What's doing that? It's just a description. And likewise, would a graviton be a description? It's not talking about how it really originates. And I don't think the origin of anything is known from a secular viewpoint. So that's all. You're right, there's got to be a beginning point. But science is not going to find it.
Maybe someday,
Yeah.
because if Colossians 1:17 is solid and holding things together, if the sun goes away in 8.5 minutes, if God's holding everything together, the earth should keep going around. If you see what I mean.
If he chose,
Yeah.
but the mechanism as we understand it, this gravity, whatever it is leaving the sun and following the earth until it would get shut off or something. So yeah, it's all part of the story. How little we really know. Yes, ma'am.
Going back to the question about the effect of the earth and the moon. And I have read that one of the, I guess, explanations or one of the reasons we can kind of prove that we have a young earth is that the moon is gradually moving away from the earth. And if the earth were millions of years old, the moon would actually be touching the earth. But if gravity is what is holding the moon in orbit, why is the moon gradually, and if gravity is constant, why is the moon gradually moving away from the earth?
Yes, that's a good question. That involves lunar recession, as we call it. The earth and the moon are coupled together by gravity. Or we could say that they are tidally coupled together. The earth pulls on the moon and vice versa. Anyway, that interaction is slowing down the earth very slightly. And as it does that, the earth is actually pulling forward on the moon's orbit, causing it to spiral outward. It's a tide thing. And currently the moon is going outward very slightly, about 1.5 inches per year. Of course, in 10 years, that's 1.5 feet, and this continues to grow. And you say, well, that's still not very much. But if you go back in time with this, 100 years or 1,000 years, then the moon would have been recessing much more. It's non-linear. If you get the earth anywhere near the moon, then the moon recesses much more. Anyway, when you do the math on that, you will find out that at current rates, and from what we know about the tides, the moon would be right here, it'd be right up against our nose in about 1.5 billion years. But they say that the moon is 4.5 billion years. And it can't even be 1.5 billion because it would end things here. You can't have the moon that close to us. So again, I only think the moon is about 6,000 years old. But if you extrapolate back with what we know about that tide connection, you run into trouble. That whole idea of that non-linear motion of the moon is going to be described in the next copy of your Foundations magazine that this organization puts out. So you can see if that explains it any better, but we have a whole article coming out on the moon everything you'd like to know about the moon. So you'll see more about that. So yes, there is that connection. You know, in a young Earth view, the moon has moved outward, but since the beginning of time, only about 100 feet. So it's really insignificant. But you can't avoid that. They are tidally locked together. Thank you.
So we have the moon moving away from the earth. And during the time of the flood, it would have been some distance closer, whatever that happens to be, during the flood. Do you have any perspective or thoughts on how that would aid and abet the flood? Because of the greater tides that you would have, because of the greater gravity strength that we have?
That affected the changing position of the moon at the time of the flood 4,000 years ago would be negligible. Because you're only talking a few hundred feet, less than that the moon has moved, and
Yeah.
you'd have to have many miles before you'd have anything there.
All right.
But since you mentioned the moon and the flood, that's interesting. The moon was in the sky during the flood. It's always been there. And during that year-long flood, you have shoreless oceans. You have water everywhere. Talk about tides, because the earth is turning beneath that moon. And so you'll have 2 high tides and 2 low tides every 24 hours. And so you would have large tides going on the planet. And that would add to the ocean currents, and that would add to the slurry and the motion of sediment. And when we see these places where there are many multiple layers of sediment and sedimentary rocks, maybe some of that is due to daily tides that were occurring during that year-long flood. Not only surges of current coming in and bringing layers, but you also have that effect of tide settling of material.
And that added to the Coriolis effect.
Yeah,
That's
yeah. So it,
just another adder factor to make it such
another
a violent
unknown
place.
variable. Yeah, and I'm not sure that that's been studied by anyone, but that'd be another track. Yes. Yep, good thought.
Okay, what, no more questions?
Did you have?
I'm gonna set Fred up for a question.
This afternoon, Fred hosts a radio program called Real Science Radio. And he and his co-host were talking about the DART expedition to the, well, the acronym is DART, I think it's DART. There was the projectile used to impact an asteroid about 2 weeks ago.
Yes.
And the result of that was that it changed its trajectory by a small amount. And it, from what I remember hearing in the news and in the papers, it created kind of a comet of its own because it dislodged a lot of dust and it's created a plume, you know, trailing the asteroid. So we're now going to have I guess a comet debris field that the Earth might pass through in the future. Of course, they said that nothing would impact the Earth from this experiment they were going to do, but as we've found out from experimentation by our government on economics, things are not always as they are anticipated to be. So I would like to set Fred up for any further questions about the DART project or things related to potential that asteroids and comets are potentially from the Earth during the Great Flood. You know, that they were part of the ejecta, that was created from the fountains of the great deep, possibly causing escape velocity if we're both material, you know, all types of material, including water and frozen comets.
Two thoughts there. The first one is that collision where we slammed a object into an asteroid. That was really just a test to see if we could hit one. The deflection that we would give it would be insignificant. It'd be like a BB hitting an army tank because asteroids are pretty good size, but it showed that that could be done. You know what they're afraid of is that some stray object that could destroy the Earth is going to come our way, and then they would have to get real serious about deflecting it. I would simply say that's not in God's plan. He's not going to wipe out all the life on Earth with some random collision. There's just too much empty space, and that's not his way. So I don't think that's a concern of ours. Your other idea, the origin of comets. Boy, there are hundreds of comets. Whether they are connected with the flood or not, that's an open question. I'm always a little bit wary of connecting the Genesis flood with outer space phenomena, that it caused craters on Mars and outer planets. We know that there was a flood. We know that the fountains of the deep were broke loose. We know that the Earth got faulted and all kinds of cracks in the Earth's crust. Whether that's responsible for craters on the moon and things going into space, I'm not so sure. I just say we need to be careful about that. It's certainly a possibility, but not a certainty. Good questions, folks. Thanks a lot.
Well, thank you. Well, that was normal, amazing information here. So anyway, I guess that completes the formal part of the evening. If you would like to continue carrying on a conversation with Dr. DeYoung, he will be here till we close the building at 9:30. Or you will be here, right? Okay. In the meantime, we have some refreshments in the back. You're welcome to partake and talk and have fun and fellowship. And we'll just start trying to leave the building by about 9:15 so we can be out of here by 9:30. So thank you for attending the meeting and have a